Okay, so at the end of the last video, I gave you a question to calculate the correlation coefficient with the transformed data. And the answer is A. So because with the original data, we already calculated the correlation coefficient and obtained minus 0.7559. So because the correlation coefficient is unit-free, after changing the units, it should not change. So as a result, it should be the same. But even if you calculate the correlation coefficient using the covariance and standard deviations, they'll be the same. Like let's try this. So remember, standard deviation, like after linear transformation, the standard deviation changes like this. Plus b does not appear at all, but a is preserved as a multiplication. So the new random variables, transformed random variables standard deviations are calculated like this. 1.8 times the original standard deviation, which was 15, and 1 over 1000 times the original standard deviation. So plug them in here, then you are going to get these numbers. By the way, it is also without doing this, it is clear. So standard deviation in standard deviation W, 1.8 is multiplied. In standard deviation of Z, 1 over 1000 is multiplied. And these two are multiplied at the same time in the covariance. So it will be cancelled out. So in the end, you are going to get the same correlation coefficient. So same numbers in the linear transformation will be multiplied in the numerator, denominator. So there will be no change in the correlation coefficient. And as I said, this is more meaningful because negative sign is about the relationship, direction, and the absolute value is about the strength. So the correlation coefficient both captures both aspects of our relationship, the relationship that we are interested in. Okay. So then let's go to Excel and see how we can calculate the correlation coefficient. So we have country names. Let me minimize this cell. It's not important. So this one is temperature. So also I will reduce this part. And this is GDP per capita. I have Celsius tab. In Celsius tab, temperatures are in Celsius and GDP per capita are in dollars. And I have another tab, Fahrenheit, which has temperature in Fahrenheit. And GDP per capita does not change, right? I just left it in the same way, So I only change the temperature to study what happens. And what you can do here is, for example, I will first calculate standard deviation of each variable. So let me increase this. Let me increase the size. So I used stdev.p with the data range. So remember, .p is the population formula. But if you use sample formula, I don't remember the last cell. Oh, excuse me. So B2 through B184. Then this is sample standard deviation. Sample standard deviation, population standard deviation. So let me write sample standard deviation and population standard deviation. And you can do the same thing for GDP per capita. GDP per capita has much larger standard deviation, right? So remember, we calculate temperature standard deviation only using temperature, and GDP per capita standard deviation only using GDP per capita. But when you calculate covariance formula has also population version and sample version. Let me show you how we do it. Oh, sorry. Excuse me. Oh, my mistake. Sorry. Covariance dot P, and what? First, you have to choose temperature variable, column B, and comma, and then choose column C. You have to specify distinguish two variables using comma. So then you have this covariance. Covariance is minus 36,000. As I said, minus means something, but 36,000 doesn't mean anything. Similarly, like if you calculate, covariance for sample version, and then covariance dot S, and choose the same data, then it is slightly different. The sample version and population version are slightly different. Okay, so now then let's see. I will calculate population correlation coefficient and sample correlation coefficient. By standardizing, the covariance will be standardized by this times this. This will be your correlation coefficient, which is minus 0.3. And sample version, let's compare that. Let's compare with the population version. This will be standardized by 2 standard deviations to the corresponding formula are the same. So, in the correlation coefficient, we do not distinguish population formula and sample formula, because in the end, the denominator n-1 or n will be cancelled out, because when you use n or n-1 in covariance, also you use the same denominator in the standard deviation, and you are going to divide them one by the other, so they will be cancelled out. So correlation coefficient has no difference in those two formulas. So, and shortcut is correlation. This formula will calculate the correlation coefficient in one step. So as they should be, they are the same thing. So I reiterated what we have done here. Okay, so then let me copy this and put it here. Up. So I am copying the formula to the data in Fahrenheit, right? I am changing the data into Fahrenheit, and I recalculated the same thing, same measures. So standard deviation is now 14.8, which was 8.2. So 8.2 becomes 14.8 because we changed Celsius into Fahrenheit. So now the scale changes, so the standard deviation changes. But this side does not change because I did not make any change in the GDP per capita. GDP per capita remained the same. So the same thing, same numbers, the same. And covariance are different again. The covariances are different because it was like minus 36,000, but now it is minus 66,000. So it increased a lot because it's now in Fahrenheit, right? As much as standard deviation is inflated, covariance is also inflated. So the inflation rate is the same for standard deviation and covariance, right? Because it went through the same linear transformation in the temperature. But in the end, because they are inflated proportionally, correlation coefficient is the same again. When you standardize covariance with standard deviation, it will be the same. So the correlation coefficient is the same no matter what you use. Okay, so you may try what happens if the GDP per capita is denominated by 1000. That is also possible, but in the end, so standard deviation, this will change, covariance will change, but correlation coefficient will not change. So that is the power of the correlation coefficient. That is why correlation coefficient is useful and informative. Okay, thank you for watching, and I will use another example and another data set in the next video. See you later.